Thank you. So my name is Peter Thoman, and I am chairing this first paper session on correctness. Our first speaker in this session is Jan Patrick Lehr. He's a PhD candidate with the Institute for Scientific Computing at the Technical University of Darmstadt. And he actually previously visited the ROS compiler group at LLNL for half a year. And his main focus is on performance analysis and correctness tools for HPC applications. So it should be a good point to continue on from the talk we just heard. So today he will be presenting his work on compiler-assisted typesafe checkpointing. And so, yeah, please go ahead, Jan Patrick.
Yeah, thank you for the kind introduction, Peter. My name is JP Lehr. You can actually find me on Twitter under that handle at JP Lehr. If you want to reach out to me via email, there's also the email address, and also the email addresses of all my of the co-authors. I think actually Alexander is also in the audience, so that's cool. Yeah, so I'm going to talk about our work on compiler-assisted typesafe checkpointing. And first, let me show you why we looked at that. So if we look at current checkpoint restart libraries, like we see, for example, the VeloC library here in the example, we have an allocation called PA that allocates some number of doubles, for instance. And then how the library works is that we call a function that protects that memory region. So we're just choosing some ID for it, and then we're giving it a pointer to the memory region, and we have to specifically tell the library how many elements of which type or how large these base elements are, such that the library internally will just calculate the number of bytes it would need to store. And then whenever we call the function checkpoint, it will actually just memcopy all the this number of bytes into the internal buffer or into the file that we use for checkpointing. And then eventually we can free or unregister the memory region again from the library. Now, if we look at this interface, it's actually pretty obvious that we can do just some usage errors here. So for example, if we consider still we have an allocation that has n times, that holds n integers, and now we misspell, for example, the number of elements that we want to store simply by putting in an x instead of an n here, we would actually miscalculate the number of bytes. The same is true if we confuse the type of that allocation just because we didn't think too much about it. So if we look at the actual memory, what happens with these sorts of errors, now let's consider an allocation that holds 3 integer values, and we assume 4 bytes per integer here, and they're packed together. So we have this allocation that is valid in a sense. Now, if we store too many elements, if we store too many elements, then we would actually illegally read behind the allocation at the point of at the time point when we actually do the checkpoint. And if we restart, we would actually illegally write behind the allocation. Both would either result in a crash if the memory region here is actually not part of the process, or maybe even worse, it will be a silent error because we just overwrite some useful memory that we're using for different variables in our program. So the error might even be unnoticed. In the case of too few elements, like depicted here, we would actually not capture some valid and some reasonable data at the time of the checkpoint, but then at restart time, we would actually not initialize the memory. And so our application may crash or might just compute bogus results, which again, would probably be even worse. But so from these examples, we can actually derive different types of errors. And we sort of named them as the element count error, the data type error, and then because of this 3-stage interface, we also we have something called the change allocation before checkpoint error. The first two I showed examples for in the previous slides, which just, you compute the wrong number of bytes eventually. The third one here is consider that you registered in a memory, an allocation, but then you freed it and then you run the checkpoint routine. So you would actually read memory that has already been freed by the operating system, again, leading to potential problems. Thankfully, all those types of errors can actually be detected if you're using allocation tracking. So we decided to, let's implement that and see how well we do. Our approach here is that we implement a mechanism that would actually allow you to state certain requirements on memory regions. So we thought a little ahead here maybe. And then for every checkpoint restart registered memory region, the developer or our system actually states requirements such as the type and the length of the allocation that is assumed by the developer. And then at runtime, we can actually check the given requirements, whether it's valid or not. And if it's valid, we continue with the execution of the checkpoint. But if it's not valid, we can actually abort the execution and print an error message to the user stating, this was the assumption, this was the requirement, but this is what our runtime actually found in memory. So it's easier to debug the application. Now, this is similar to what has been done in MPI type checking, and I put a reference here with the MUS tool. And so in that work, we created a tool called TypeART, and now we're using this implementation and extended it for our purpose here. So to look at the TypeART tool, how it's actually implemented and how it's working, we can look at the schematic. It's an LLVM, Clang LLVM based tool. So we just normally run the source code through Clang to generate the low-level IR or the IR that is used in LLVM. And then we implemented several passes that do analysis and transformation. During this analysis, we actually gather type information from the different allocations and store that in we just say typedb. And we capture the type layouts as well. So if you have a struct, for example, we actually capture the different members of that struct and the different offsets to the members, so that at runtime we can use this information. And then in the transformation pass, we actually insert instrumentation calls to grab the different allocation sizes for the different memory regions. And then at runtime, the application does, through the instrumentation, actually do allocation tracking, and we can query the runtime for information about the different memory regions. So the instrumentation that we insert kind of looks like this. So if we have a malloc call here that allocates %0 bytes, so %0 is the variable, so to speak, that holds the number of bytes that it should allocate, we insert a call that computes the actual number of elements that is allocated here. So we know from the example that we have a float here. And so we compute %0 divided by the size of the float to get the number of elements, what we refer to as the extent. Then we insert what we call a type ID. So every built-in type has a predetermined type ID, and for user-defined types, we create them during compilation. And then we capture the pointer. We derive the type information from the bitcaster that would actually store the type of the allocation. And now with that information in our runtime, we can pass in a pointer and ask for the type information about that pointer. How we use that in TyCart now, the typesafe checkpoint restart extension that we provided is, so we insert the instrumentation here using just the regular TypeART transformation and analysis passes. And then our runtime actually implements functions that would intercept the calls to the checkpoint, or that wraps the calls to the checkpoint restart libraries. Before calling the backend, it takes the pointer that is passed, asks the TypeART runtime for the type info for the allocation information, and then does the checking, does the validation of the requirements. And then if they succeed, it would actually call into the backend. So currently we support the fault tolerance interface and the VeloC checkpoint restart libraries. So the TyCart interface that the user would actually use is very similar to the to what we saw in the first example. So we have a ty protect, we have a ty checkpoint, and we have an onProtect function here. We pass pretty much the same parameters, but now please note that we here just type the regular type that is used in the application and not use the size of operator. Because those interfacing functions are actually implemented as macros and they are transformed to something that looks like this. And I'm sorry for the maybe a little overwhelming text here. So we insert a pointer that is of the type that we're actually asserting, and then we're inserting what we call a stub function, sometimes also referred to as fake function, where we pass in, again, the address and then the pointer. We use the pointer here mainly to capture the actual type that we are asserting. And we forward count and ID. The call to this function, to the stub function, is then replaced in the LLVM compiler pass by a call to the actual implementation of the TyCart assert function in our library using the type ID that the LLVM analysis pass that we run in TypeART actually generates. Now, considering user-defined types, it's a little more interesting because so far we only considered built-in types. So here, consider that we have a struct, it's called vec, it has two data members, an integer size and a double pointer data. Now, if we write the ty protect macro like this, and we actually want to checkpoint the size member as one integer, we run into the problem that we actually have ambiguous addresses here, or ambiguous type information. So in memory, it sort of looks like this. We have the struct vec v here that is allocated, and the first part of it being the size member. Now, the starting address here actually has two type informations. And I think I missed a slide actually. Here we go, sorry. So the start address here is actually the same for size and the overall struct. Because in TypeART we only store a single type info for a pointer, we actually have an ambiguous type info here. To solve this problem, what we do is for user-defined types, because they are constructed from built-in types, we can actually do a recursive subtype resolution. What we do here is in that situation, the assertion fails because TypeART would say it's an allocation of type struct vec here. But now, because it's a user-defined type, we get the type layout for the specific user-defined type, and then we iterate through the data members of the ambiguous address just to find that as the first data member, the vec struct actually has an integer member, and so we can now check one integer at this address, and the assert succeeds. The pseudocode here is pretty much what I just said. So if the address is not the asserted type, we check whether there is a user-defined type. If that is so, we actually get the member type of that user-defined type, and then we assert the subtype here. We refer to this as a weak assertion, as compared to just the assertion or the strong assertion for the built-in types. Now, we evaluated the approach on a collection of benchmarks and tools and target codes that we have. We run the experiments on the Lichtenberg high-performance computer, which is the old one. Now, on Monday, we saw that the successor system, LB2, has landed and has entered top 500 at place 93, but quite happy to get our hands on that in some time. The results denote the median over 10 consecutive runs, and we have a standard deviation of 3% or less, except in the combination of FTY and TyCart in the specific driven cavity benchmark, where we have a standard deviation of about 6%. We run different C++ and C experiments. The first three here are sequential programs, and the last two are MPI parallel programs. We use low MPI parallel ranks here because the TypeART runtime or the TyCart runtime do not add any MPI communication, so there's no issue with scaling this up. We capture a couple of compile time numbers for analysis. So here, for example, we see how many heap allocations we instrument and how many heap deallocations we instrument. Also, how many globals we actually have to instrument, or and the percentage of that number of the number of total globals that we actually are able to filter out from the instrumentation. Also stack allocations here, and again the percentage of stack allocations that we are able to filter out. The filtering is performed currently with a translation unit local data flow analysis. So if we find that an allocation cannot reach one of the assert functions, we exclude that allocation or that pointer from measurements. If we cannot verify that we would not, that this pointer will never reach one of the stub functions, we actually have to capture it. Also, we have the number of regions that are registered here and the actual checkpoint size. Now, if we look at the runtime that our approach, the runtime overhead that we introduce, here it's important to note that the left bar is always the target application with just the checkpoint restart library added, and then the bar left to it, it's with our TyCart memory tracking. So you should always compare the two bars adjacent to each other for the actual overhead that our tool introduces. And so we see here that for most of the benchmarks, we actually do not add significant overhead. One exception is this particular code at the end here, where we actually increase the runtime by a good number of about 70%. And I will discuss this in 2 slides a little more. The same picture we have here for the memory that we introduce in addition. So again, please always compare those two bars next to each other for the additional overhead that our approach introduces. We see again that we do not add significant overhead in most of the benchmarks, again, except the EOS MBPT application here. We capture a number of runtime statistics as well. And if we look at those, we see the reason for the tremendous runtime overhead we introduce, or not the tremendous, but the significant runtime overhead in the EOS MBPT app, because we actually have to invoke the instrumentation functions roughly 32 million times, and for the heap allocations and for the stack allocations roughly 50 million times. So that is quite significant, and the maximum number of pointers we track at the same time is about 16 million. So that's quite a large number, and that is also the reason why we add that much overhead, the 70% runtime overhead in the EOS MBPT app, because of all the additional calls. And because we track so many allocations, we actually see that memory increase. So what we saw so far is that TyCart allows for an to effectively check the validity of the stated type requirements and for the CPR calls. I think we have that within reasonable overhead margins. And our approach works with C and C++. What we currently do not support is incremental checkpointing because we want to strictly enforce this partial initialization of memory. Enforce that we prevent to partially initialize memory. Right now also the user-defined types, the handling is somewhat limited in its configurability. So we want to play around with that a little more and allow like a resolution level to specify how many subtype resolutions you would actually do. And currently we do not handle restart explicitly because we rely on using TyCart to capture the data, and then it would be safe to restart the data as well. So to conclude, we have seen a tool that allows for typesafe checkpointing for two different CPR libraries. It's based on what we call type asserts, where you can specify these assertions on memory regions. And in our opinion, we introduce reasonable runtime and memory overhead. It's open source. It's available at github.com in our repository. It's BSD3 class licensed. And yeah, I'm happy to get feedback and you play around with it if you'd like to. And some references. Thank you.
Thank you very much, JP, for this very interesting talk. So I haven't seen any questions posted so far in chat, but I have a few questions. So the first one, it's probably not that relevant in practice, but how do you deal with union types? Because obviously this could probably not work if you have one type ID at each memory address, right?
Yeah, so I don't want to say if I was afraid of that question, but it's a valid question. So I remember that we had quite a conversation about that. But the union types are actually represented in LLVM-IR as a struct type. So we capture a struct with some with the name of the union and see that as the user-defined type. So we can check for unions at that level. However, we would rely on the user, on the programmer, to actually make sure that she accesses the right type in that union and knows what the actual stored type was. So we do not currently support unions in the full extent that would be maybe loved by some users.
Did you actually encounter union types in the codes that you investigated?
At least not in the sense that we found errors with them. Let me put it that way.
Okay, thank you.
Yeah.
So there has been another question. How difficult would it be to teach TyCart another checkpointing API?
So that is a very good question, and that depends a little bit on the API of the checkpointing library. So we looked into HDF5, for example, a little bit, and saw that HDF5 would probably need a little more attention. Every library basically that would use let's say a low-level interface like we saw here with VeloC and FTI would work pretty well. I have to say that we actually support the basic FTI user-defined types as well. So you would actually, for FTI, you would actually register, or you need to register user-defined types in the FTI library. And in TyCart, we again have a wrapper for that so that we can make user-defined types aware in the FTI runtime. So I guess it's doable, but it obviously depends a little bit on the API of that CPR library.
Okay, thank you. I have another question. You presented some results concerning the runtime overhead of your approach, but the main goal is, of course, to increase safety and find usage errors. So did you actually find any usage errors with the tool during the process of evaluating it?
Yeah, that's a very good question. And yes, we did actually. But the interesting point here is that we use VeloC in a project of ours that is similar to the to sort of the whole program auto tuning part that Leo presented. And the errors that we found were where we relied on some information that we received from the programmer, how large certain allocations were. And so we checkpointed those allocations given those sizes, and we found that for the problems we were running, those weren't actually initialized in those dimensions. We reported that to the project partner, and he said, yeah, we know, and this has been addressed by now. So it had at least some benefit also for the actual applications.
Okay, thank you. If there are no further questions, then I think we can move on to our second speaker. And our second speaker in this session on correctness is